Hello everyone and welcome back to the LNG Academy. I'm your host, Mehdy Touil, and for any new listeners, I want to reiterate the vision of the LNG Academy podcast, which is simply spread LNG education to the world. Today we are excited to have our second guest on the show, Phong Dang, a recognized expert in the LNG industry and one of the best engineers I had the honor to work with. Phong, thank you very much for joining us, and it's a pleasure to have you here today.
Thank you very much for your kind introduction, Mehdy. It's much appreciated.
You previously worked as a process engineer on world-class projects like Gorgon and Wheatstone LNG in Australia. Nothing, however, had prepared you for the brutal Arctic conditions of Yamal LNG and the phenomenal performance of the trains. How was the highly successful C3MR technology adapted for Arctic conditions?
Yes, Yamal LNG was the first facility where the C3MR technology was adapted for Arctic conditions. We'll discuss some of the innovation that were successfully employed in this podcast. In addition, we'll provide a tip that could help to improve the integrity of the main cryogenic heat exchangers at other facilities. In the Arctic, the ambient temperature can vary between minus 40 in winter to plus 25 in summer. The swing is therefore much larger than in warmer climate, where typically it swings between plus 20 and plus 45. Therefore, the first and most important innovation at Yamal was to mount the propane, LPMR, and HPMR compressors on a common shaft driven by a single frame 7 gas turbine. A second parallel compression train driven by another frame 7 gas turbine was provided to enable a single train to have sufficient power to produce 5.5 million tonnes per annum of LNG. To date, these are the largest C3MR trains currently in operation. With the 2x50% configuration in winter, the propane system required less power, hence more power is available for the MR system, while in summer, the propane load will increase and ultimately limit the LNG production. Hence, the LNG production can be maximized year-round by effectively utilizing the power available as the load shifts between the two cycles. The second innovation to enable the Yamal LNG trains to maintain its Tech-Max production curve for approximately 60% of the year was to have the LPG extraction unit up front of the liquefaction unit. Hence, the natural gas is liquefied at much higher pressures than in trains that utilizes an integrated scrub column design. At Yamal, the natural gas was liquefied above the critical point. Higher pressure leads to higher liquefaction efficiency. Yamal introduced some new innovations that wasn't seen in older facility, such as the installation of check valves in the MR return line, which were required to prevent backflow from one train to the other. The check valves provided another benefit when both of the strings tripped by preventing large amount of hot gas from the discharge of the LPMR compressor being released back into the shell of the MCAG when the hot gas bypass and anti-surge valves open. In facility without a check valve, a trip could lead to a rapid increase in the shell side pressure and opening of the vent at the top of the MCAG, often causing high reverse pressure drop across the shrouds covering the tube bundles in the MCAG, which could potentially lead to the damage of the shroud and hence liquid MR bypassing the tube bundle, leading to a loss of efficiency. At Yamal, the check valves were proven to be effective at minimizing reverse flow. Therefore, facilities that are at risk of shroud damage should consider installing a check valve in the MR return line.
So, what were some of the innovations used to enable Yamal to successfully start up in winter conditions?
Both Train 1 and Train 3 were successfully started up during winter where ambient temperatures were below 0 degrees Celsius. The success could be attributed to great planning and collaboration between the fabrication yards in Asia, the engineering contractor Technip, and the operating company Yamal LNG. For example, some measures taken between the three parties were high-pressure leak tests were performed at the fabrication yard, which reduced the number of tests that needed to be completed on site. Pipework was cleaned, dewatered and pre-dried by the engineering contractor using nitrogen prior to handover. This is a practice that's not normally done in warmer climate. In addition, temporary insulation were fitted to process line in the propane, MR and fractionation unit that did not need insulation during normal operation. Air coolers in the LPG extraction unit, propane and MR systems were covered with temporary tarpaulin to minimize heat losses during defrosting. Defrosting performances were not only based upon moisture reading, but also upon system temperature, which isn't a focus in warmer climate. But at Yamal LNG, we ensure all the systems we defrosted reach a temperature of plus 10 degrees whenever possible. While these measures were effective, an improvement that should be considered for future design is to include bypasses around air coolers in both the propane and MR system. This will open up the possibility to defrost both the propane and MR system and maybe even the MCHE dynamically, thereby significantly reduce the amount of gas flared during startup. Reducing flaring should be a focus for all future LNG plants, since it will not only reduce greenhouse gas emissions, which is very important, but it will also preserve valuable product for export. In addition, as we learned at Yamal LNG, reducing flaring during startup can also safeguard the integrity of the flare system. As you're aware, Mehdy, during the startup of Yamal, we damaged the flare towers by flaring large amount of gas. As a result, we had to revamp our entire startup sequence, including the way we cool down our MCHE.
What are some of the adaptations required to operate the Frame 7 gas turbine in Arctic conditions?
The main adaptation required for the turbine to operate at Arctic conditions was the anti-icing system. The objective of the anti-icing system is to prevent moisture in the air from freezing, which could potentially block the filter house, leading to a loss of power output from the turbine, while ice particle that enters the air compressor could damage the engine's blade. The anti-icing system at Yamal kicks in when the ambient temperature falls below plus 3 degrees C, using an inlet bleed heating valve, or what we call IBH valve. The IBH valve recycles hot air from the compressor's discharge to the inlet of the filter house. Recycling of hot air to maintain the inlet temperature approximately 10 degrees C above ambient temperature will lead to a loss of power output from the gas turbine. However, the impact was only relatively minor, since at temperatures below minus 5 degrees, the capacity at Yamal was limited by hydraulic rather than power available. Another important function of the IBH system during low temperature was to make the air less dense by making it warmer, and hence increase the actual compressor's operating envelope. For combustion stability, the IBH works in tandem with the IGV to extend the premix steady state range.
Was there any process operational problems that were unique to Arctic conditions?
LNG plants tend to operate the best when it's operating close to its Tech-max curve, which is what occurs during winter. However, we still encountered some problems, such as during startup, it was difficult to generate sufficient pressure to overcome the static head required to flow liquid propane from the accumulator to the subcooler. Yamal uses a quench system to assist the desuperheater to keep the propane compressor cool. The quench was taken from the outlet of the subcooler. Hence, there were a few occasions where the propane compressor was overheated due to loss of quench. This issue was overcome by maintaining some non-condensable in the propane system during startup and by utilizing the bypass around the propane condenser when ambient temperatures were very cold. Another issue we faced during winter was the operation of the air coolers, particularly the LPMR compressor aftercooler and the propane subcooler. The outlet temperatures from these coolers were controlled by turning fans on and off. This created several problems, and in the case of the LPMR compressor aftercooler, it led to several gas turbine trips. When a fan was turned off, it led to both the suction pressure and temperature to the HPMR compressor decreasing. This led to an increase in seal gas flow through the HPMR compressor's primary seal gas vent, hence an increase in pressure drop across the vent's orifice. It was suspected the sharp decrease in suction condition caused the shaft to move, and the HPMR compressor's seal was unable to compensate for the movement due to potential issues with the sealing material used, which lost its flexibility from the cold temperatures. As for the propane subcooler, switching a fan off led to a decrease in the suction pressure of the LP stage. As a result, CCC needed to open the LP stage anti-surge valve to prevent the compressor from tripping on low suction pressure. This led to a loss of efficiency and sometimes caused unstable low pressure operation. Some potential solutions to rectify these issues for future plant design include providing bypass around the air cooler, which could also help with dynamic defrosting of the system as discussed earlier, or provide some variable speed fans in combination with the on-off fans for key air coolers such as the LPMR compressor aftercooler and propane subcooler. The variable speed fan would provide much tighter temperature control and thereby minimize these issues.
At Yamal LNG, blackout events were a major concern. Can you explain why?
Yes, Mehdy, blackouts were a real concern because of loss of winterization due to loss of electrical heat tracing. Hence, should a depressurization sequence be initiated, it could have had a catastrophic impact on the mechanical integrity of the low temperature carbon steel piping had the temperature go below the minimum metal design temperature during depressurization. At Yamal, to prevent this, in the event of a train shutdown, the operator will have approximately 160 minutes before needing to launch a preventive non-emergency depressuring of the train to avoid brittle metal failure.
So, final thoughts?
Final thoughts? We're seeing a renewed interest recently in Arctic LNG projects like Alaska LNG and Key Lake LNG projects in the US. I think these projects could learn a lot from the success of Yamal LNG. What do you think, Mehdy?
Definitely. That is something that they need to consider. Yes. So thank you, Phong. This has been a great technical overview of the Arctic LNG. Thank you everyone for tuning in, and we'll catch you on the next one. Goodbye.